Hi, everybody. We're picking up where we left off with the electromagnetic spectrum. And um, everything that is on the electromagnetic spectrum, we can actually call light. And I'm not just talking about visible light, I'm talking about all types of light, and all of them are included on the electromagnetic spectrum. Okay, we only have a very small portion of the electromagnetic spectrum that is actually visible to the human eye. And if you look at this bar down here, you can see this little sliver that's cut out, and that's visible light. That's what we can see, the Roy G. Biv visible light spectrum. That's the only thing that humans can detect. But all of these other types of light are included in the electromagnetic spectrum. Radio waves, microwaves, infrared, visible light, ultraviolet light, X-rays, and gamma rays. Okay, since we can consider them all light, they all travel at the speed of light in air or a vacuum, 3 times 10 to the 8th meters per second. Okay, but all of these light waves, they have their own wavelength as well as their own frequency. And if you look at the low end, this is the low energy portion of our spectrum, you see things that you consider harmless, like a radio wave. Okay, radio waves are very low energy, they have a very long wavelength. If you look over here, this bar represents the wavelength of the waves, okay, how long they are physically. And long radio waves can be, in the 10 to the second power. So that's, 500 meters long, 100 meters long, so we have long radio waves. Then we have going into the microwave portion of this. Now, I'm sure tons of people in your life have told you not to stand near a microwave because, it'll fry your cells and all of that, and they'll give you cancer. But if you look at the electromagnetic spectrum and you actually understand physics, you would understand that a microwave has a lot less energy and it's a lot larger than even the color red. Do you know anyone in your life who is afraid of the color red or the color yellow or any of the colors of the spectrum? If you're standing near something that is any color, it has more energy and is more quote unquote dangerous than a microwave. Okay, so that doesn't mean get in a microwave because that's a totally different scenario. Don't do that because that will boil the water in your cells. Not a good thing. So here's a different graphic of the electromagnetic spectrum. Okay, and you can see things here. And I wanted to bring this up too because here we have cell phones. Cell phones emit radio waves, and those are very low energy compared to even visible light. Look at where visible light is on this spectrum, right over here. And your phones have a very low energy, long wavelength um, wave there. Okay, so as you travel along the electromagnetic spectrum, we have low energy radio waves, then microwaves, infrared. So that's, you've ever seen infrared goggles that detect heat signatures of like people, you know, wear them at night to see, animals hiding in the woods and stuff like that. So infrared, and then we have the very small visible light spectrum, and then we have ultraviolet light. Now, this is where we start to get into the more dangerous types of waves. Okay, everybody knows that ultraviolet light comes from the sun. It's what makes you tan, but it also is small enough to get into your cells, okay, and mutate your cells. And this is actually where we start to get, damage, where the ultraviolet light mutates your cell, and then you could get skin cancer. So once we get towards this end of the spectrum, this is our high energy light waves, okay? And we all know ultraviolet light's not a good thing to be around that too much. That's why we wear sunblock. X-rays, it's never good to get a bunch of X-rays over and over again because that's too much radiation for your cells, can damage your cells. That's why the dental hygienist and the people in the emergency room, they leave the room to push the button in order to do your x-rays because this is damaging to your cells. And then the highest energy we have here is the gamma rays, which come from, the sun. And you all know if you get exposed to a gamma ray, you turn into the Incredible Hulk. So, or it actually just destroys your cells. So you don't want to do that. All right. So low energy, relatively harmless waves on the left side of this spectrum, high energy, high frequency waves on the right side of the spectrum. And you can see how they kind of show that with how the wavelength is getting smaller and smaller as we go along until we have a very high wavelength, short wavelength, high frequency, okay? High frequency wavelength over here. And this is low energy, low frequency. So you'll see an inverse relationship between wavelength and frequency. Now, remember, the speed of the wave in the same medium remains the same. This is a concept we went over yesterday. All waves of the same type travel the same speed if they're in the same medium. So if our wavelength goes down as we go across the spectrum from the low energy to the high energy, the frequency goes up. Okay, and something that is specific to electromagnetic waves, the frequency is proportional to the energy. Okay, the frequency for an electromagnetic wave is proportional to the energy. We went over mechanical waves before, so this is an aside. Mechanical waves, things that require a medium, their energy was not proportional to their frequency, but really their amplitude. So their amplitude was proportional to their energy. And you have to make a distinction in your head between a mechanical wave that requires a medium and an electromagnetic wave that does not require a medium. Okay? So the next time someone tells you to get out of the kitchen because the microwave is on, remember that microwaves are a lot less dangerous than any color you can see. So, and these are probably the same people who lay out in the sun with no problem, but they're afraid of the microwave. So, knowing physics, you can now challenge them and tell them that microwaves are no more dangerous than any color we can see. All right. And here they actually give you a scale for the length of the wave. We see radio waves are about as long as a football field, and then you see the scale getting smaller and smaller. And this is why you know that the wave gets more dangerous as the wavelength decreases, because then it gets as small or smaller than a human cell or a human DNA. So that's why these can penetrate the cells, go through the DNA, mutate things, and then we have problems. All right. All right. So this chart is to help you figure out what part of the spectrum, the visible light spectrum to be exact, your wavelength would be in. So if you have waves of a certain wavelength, you could figure out what color they would be just based on these ranges. So anything in that range would produce the color there. Okay. We're going to try a couple problems. I'm going to do number 1 right now, but I want you to pause the video and try several of these problems up to, I think, number 6 here. And then I'll do the rest of the answers, but I want you to try them and then come back and check your answers with me. Okay? All right. So here in number 1, we have a piano. So a piano, when you push the keys, think about it, it makes a sound wave. Sound wave, just as a refresher, sound waves, they're longitudinal waves, they're mechanical waves, they require a medium. None of this we need to know for the question. We just need to know and be able to reference that information as we go. So a piano wave emits frequencies that range from low 28 hertz to a high of 4200 hertz. Find the range of wavelengths at STP for the sound waves, and then find the range of periods for the sound waves. All right, so We're going to first start with the 28 low wavelength. And for all of these questions, we're going to use our speed of a wave formula. This is good for sound waves as well as electromagnetic waves, or any wave really. And I'm going to rearrange for wavelength. So it's going to be V over frequency low. Okay, so STP, remember I told you to look out for STP when we're dealing with a sound wave. That's 331 meters per second. That's at 0 degrees C. So that's going to be our constant for this problem. And then we're going to go over 28 hertz. Okay, and then we actually get for this 11.8 meters, and wavelength is in actual length of the wave, so that's what we're looking at there. Now for the high frequency, think about what happens as frequency goes up. Okay, what happens to wavelength? Okay, where speed s remain the same, your wavelength should be going down in order to keep that speed constant. So we're going to go for the high frequency. Okay, so same STP speed for the wave, and then 4,200 hertz. So our wavelength should be very small here. It's 0.079 meters, so 7.9 centimeters. Okay, now we have to do the period. So period formula we should know from circular motion. What else? Simple harmonic motion, we used it. And period is going to be 1 over frequency. So we're going to do this both for the low frequency and the high frequency. All right, so we have 1 over 28 hertz. That gives us 0.036 seconds. Okay, period is measured in seconds because it is a time. Then period for the high frequency. Okay, but they have an inverse relationship, so you should have a low period. That came out to, if I actually show you the work, it's 1 over 4,200 hertz. So period for the high is going to be 2.38 times 10 to the negative 4 seconds. Okay, so we have all of our answers done out here. All right, so this is where I want you to pause the video and try the different problems. I'm just gonna tell you to look out for one thing. In question number 2, there's a bunch of parts. You have to use the prefix, so don't forget to, do out that prefix, otherwise you're going to be getting all the wrong answers. So megahertz, those are radio stations. I talked about it yesterday. Mega millions. Mega is times 10 to the 6th power. Okay, so you have to do all those out in order to get the correct answers. Okay, so I'm going to pause the video here. Okay, to pick up where we left off, I wanted you to try problems 2 through 6. And in problem number 2, it says the speed of all electromagnetic waves in a vacuum is 3 times 10 to the 8th meters per second. So has that special letter C for the speed of light. You could also use V if you want to. And it says calculate the wavelength of electromagnetic waves emitted by the following frequencies. Now, this is a radio wave. Radio waves are a part of the electromagnetic spectrum, and it's 88 megahertz. Okay, so remember you have to convert the mega out, so that's 10 to the 6th power. So over here we have V equals lambda F. We're solving for lambda. Okay, and so you're going to divide the speed by the frequency given, and you get the wavelength is 3.41 meters. Okay, so letter B over here, it says visible light. Visible light at 6 times 10 to the 8th megahertz. So you have an exponent plus a conversion. So you would take 10 to the 8th plus 10 to the 6th, and that would give you down here 10 to the 14th power. Okay, so same equation because it's still speed of a wave. You would take the speed 3 times 10 to the 8th divided by the frequency given, and then you would get 5 times 10 to the negative 7th meters. This question asked us also for the color of the light. Okay, so we go back a couple pages to the electromagnetic spectrum page, and it was 5 times 10 to the 7th power. And you look for the wavelength range, and 5 times 10 to the 7th power would, negative 7th power really, would be green light. Okay, so we would go back to our question, and we would answer part B would be green color. Okay, now we have a higher frequency light. We have X-rays, which are 3 times 10 to the 12th megahertz. So again, we have to take that 10 to the 12th and we need to incorporate the mega. So 10 to the 12th plus 10 to the 16th. Right, so now we have the speed of light divided by that frequency. You get 1 times 10 to the negative 10th meters. So in all of these problems, with that constant speed of light in air or a vacuum, okay, as the wavelength went down, the frequency went up, and you could see that in all of the examples. All right, the next question, question number 3. It says, the red light emitted by a helium neon laser has a wavelength of 633 nanometers. Nano is yet another prefix. Nano is 10 to the negative 9. Okay, so 633 nanometers in air. So that's a clue. So it's a red light in air. We know the speed of light in air travels at 3 times 10 to the 8th meters per second. Find the frequency of this laser light. Still using the speed of a wave formula, V equals lambda f, but we rearranged for frequency. Divide 3 times 10 to the 8th by 633 nanometers, and you get a frequency of 4.74 times 10 to the 14th hertz. Okay, the next page. This question's kind of different. And instead of finding just wavelengths and frequencies, we're actually finding physical distances. So it says a tuning fork produces a sound wave. Okay, sound waves are mechanical waves. They require a medium, and they would travel at the speed of sound, 3.31 meters per second at STP. Okay, but we don't know if this question is at STP, but that's just general information you should remember. All right, so I'm also going to write down it's a mechanical wave. All right, so they also tell us the frequency is 256 hertz. The wavelength is 1.35. Okay, so we have frequency and wavelength. Part A says calculate the speed of the wave in air. Okay, so V equals lambda f. We have wavelength times frequency. You get 345.6 meters per second. So you can see by the difference in the speeds, we are not actually at STP. It's actually a little warmer wherever this problem is taking place. Okay. Now in part B, it says, how far will the wave travel in 1 hour? So far is a physical distance. We're going to be looking for delta S. How far did it go? And to do this, we can use our old average speed formula. So average speed is distance over time. We're solving for distance. Wave won't accelerate, so it won't speed up or slow down if it stays in the same medium. So this is why we can we could use our average speed formula. So we're using the speed we calculated in part A. We have our time, but this is going to be in seconds, not hours. So you take your speed times time and you get the actual distance the wave traveled in 1 hour. All right, now in part C, it says, how far will the wave travel in 1 hour in a vacuum? Okay. Recall what we talked about for a sound wave, a mechanical wave in a vacuum. Okay. Mechanical waves require a medium to travel through. A vacuum It has nothing to travel through. It has no air, no substance, no medium. So a mechanical wave cannot travel through a vacuum. So that's why the answer to part C is 0. Will go 0 meters in a vacuum. All right, now in part D, it says, what is the wavelength of a sound wave produced by this tuning fork in water, where the sound travels at 1500 meters per second? So now we're using it's the same tuning fork, so the frequency remains the same. Okay, we have a new speed for water, and you see if we use the wave speed formula again, the wavelength will change with the changing speed. Okay, all right, so let's look at the next one. This question, you have to picture what's going on as we read through it. So it says the distance between two successive crests of a certain transverse wave is 1.25 meters. So they're giving us a distance crest to crest. Okay, by definition, distance crest to crest is a wavelength. Okay, and it says 8 crests pass a given point every 12 seconds. So I already highlighted this, that they're giving us information about the frequency. To picture this, I want you to think about crest to crest, okay, high point to high point. That is going to be a wavelength. They're telling us 8 crests pass a point in 12 seconds. And you have to be kind of savvy when you think about this, and hopefully I drew this on another page because I wanted you to say, all right, look at where all my crests are. I'm going to label them with a C. So we have crest, crest. All right. So 1, 2, 3, 4, 5, 6, 7, 8 crests. Count the number of wavelengths, full wavelengths we have here. So this is our starting point over here. So we have 1 wavelength, 2, 3, 4, 5, 6, 7. So 8 crests passing a certain point in 12 seconds is only 7 waves. It's not 8 waves. Okay, that question might have been a little tricky to understand, but the 7 waves per 12 seconds gives us the frequency. Okay, and the wavelength was already given as 1.25 meters, so we just divide, or we actually multiply because we're looking for speed. We multiply the 1.25 times our frequency, and you get 0.73 for our wave speed. Okay. All right, let that one soak in. Draw the picture out if you have to. But it's always good to draw a picture. It helps you understand a little bit more. All right, the next question, we're going to base our answers on the diagram below. It says, if the wave is traveling in the direction of positive x, so it's going this way, that's the direction of the wave speed, with a frequency of 25 hertz, find the values for this wave. Okay, some of them were clear to see. You know, we have to find the amplitude. Amplitude by definition is the distance from the rest position to the crest, or the rest position to the trough. And if you look at the dimension given on the y-axis over here, they give us 18 centimeters. So we know that's 2 times the amplitude. So part A, the amplitude is 9 centimeters. All right, wavelength. Wavelength is defined crest to crest, trough to trough, or 360 degrees on a curve. So over here, if you look at the dimension they give us in the x direction, they give us crest to trough. Okay, that's just showing us 1/2 of a wavelength. If we want a full wavelength, we have to go to the other crest. So we're going to double that distance. That's going to be 20 centimeters. All right. In part C, they ask us for the period of the wave. All right. Go back to the original information. They told us the frequency was 25 hertz. Period is the inverse of frequency. All right. So we have T equals 1 over F, 1 over 25. 0.04 seconds because period is a time. All right, the speed of the wave, now that we know the wavelength from part B and we know the frequency from the given information, you just multiply those and you get 5 meters per second for the speed. Okay, in part E, it says, in what direction will points B and C move, or which way are they moving? So remember, this is a transverse wave. The particles don't move left and right. They move perpendicularly to the wave speed. So the wave is going in the positive x direction, so the particles are going to move up and down. You have to look at the next part of the wave coming for B. So from this point to the right for point B, this is already past point B. It already went through that part of the wave. The stuff that is coming next for point B is to its left side. So this is, I don't know, we could call it the future for point B. So to the right already happened, to the left is what's coming. So now if we look at point B, the next part of the wave coming for point B is this upslope. So point B is going to move up. Okay, let's find point D and figure out which way it'll go. There is no D because it's supposed to say C. Very confusing. Okay, all right, so point C is over here. All right, remember, everything that is to the right of this point is in the past. Okay, everything to the left is what's coming in the future. Okay, so the next part of the wave that C will encounter is that downslope. So point C is going to move down. Okay, now in part F, it says identify a point that is 180 degrees out of phase with point A. We briefly talked about in phase and out of phase. In phase was when the points were one wavelength apart or 360 degrees apart on a curve. And out of phase is everything that is not in phase, right? And we just count the number of degrees between the points to determine how many degrees out of phase points are. So remember, on a sine curve, every quarter of a wave is 90 degrees. So this is 0, this is 90, 180, 270, and then back to 360 or 0. Okay, so we just have to figure out a point that is basically half a wavelength away from the point given. So we're looking at point A in the picture. Point A is over here on this part of the curve, right? And it's kind of in the middle, so we could call that like, at the halfway between like 90 and 180. So we have to get another 180 degrees away. So if I move, this is not a quarter of a wavelength, but it's really an eighth of a wavelength. So I'm going to do, this is from A to this point would be 90 degrees, okay? And then we would need to move another 90 degrees, which is another quarter wavelength. Okay, so that's 45, 45, right? So we have to mark this point with a point X, all right? And over here, I'm going to mark my point with a point for A, X.